Hello class, I'm going to record a Zoom recording for statistics for chapter 3, section 3, measures of position. Okay, and so a couple examples that they have here on measures of position, they note standard scores, which are also called z-scores. And then they also mentioned percentiles. Okay. And so sorry about that. I left my phone on. If my phone's ringing, I'm sorry I didn't disconnect that. Okay, so measures of position, a z-score. So it says there is an old saying that you cannot compare apples and oranges, but with the use of statistics, it can be done to some extent. So suppose that a student scored a 90 on a music test and a 45 on an English exam. So direct comparisons of raw scores is impossible since the exams might not be equivalent in terms of number of questions, the values for each question, and so on. However, a comparison of a relative standard similar to both could be made or can be made. So this comparison uses the mean, okay, which is x bar, the standard deviation, which your book calls S, and your calculator, your TI-84, you know that as S sub X. And let's see, compare this comparison, which uses these two, the mean and the standard deviation, and is called a standard score, or Z. We also use z-scores and later on in chapters like chapter 6, I believe. Okay. And so this is the formula. Here's your symbol. Sometimes we have sometimes I have an abbreviation, a letter, a symbol. And here's your formula. And if you're using your calculator, which most times we will, you're going to want to put a parenthesis around that because in the order of operations, PEMDAS, you want to do what's inside parenthesis first. So you want to actually subtract this before you tell the calculator to divide it. So the only way to communicate that is to put the parentheses. If you don't put the parentheses, then you will be getting a different answer. It won't come out the same. It'll be a wrong. So just be careful with that. And this formula is used for a sample, which is mostly what we're working with. Remember, if you calculate something from a population, they have to tell you in the problem that it's for a population, okay? And it's very similar, except they're using Greek letters. In populations, they like to use Greek letters of the alphabet. So remember, I had that list of Greek letters. Let me see if I have one handy. I might have one handy here. Do I? Let's see. But remember, I gave you a formula for the Greek letters of the alphabet. So let me see. Yeah, I probably put a white copy for y'all to print, because if I put this brown copy, it would, I think, eat up your print. But I have a copy of this on brown paper. But like this is sigma here. See, and there's mu. So you see that mu. Okay, so they like to use Greek letters of the alphabet for populations. Okay, again, the parentheses are important. And then it says that a z-score, or a standard score for a value, is obtained by subtracting the mean. So you see, we are subtracting the mean from the value. So this is like our data value. X is like our data value. Because we already talked about mean and standard deviation, and X, what's X? It's the data value. And then dividing the result by the standard deviation, okay? A z-score represents the number of standard deviations. The value is either above the mean or below the mean. So if it's above the mean, that means it's going to be positive. If it's below the mean, that means it's going to be a negative score. Okay, so that's also helpful to know that. Okay, and then we have a problem here. Okay, let me see if I have any other notes to add to that. I already had z-scores. I also had up here other examples, put two bulleted items. The workbook will mention deciles and quartiles. So we don't really do so much with deciles, but we'll do something with quartiles. So I just put that. Those are also measures of position. Let's see, the other thing to put down. This is important. Let me put this right here. Um, Larger z-scores have higher relative position. So higher z-scores, or excuse me, larger z-scores have higher relative positions. And then the other thing to say is that a z-score is found by converting a value to a standardized scale, and that's true. Yeah, so we're talking about at the top about they were taking this music test and then this English exam, right? And then they were talking about that they're trying to make a comparison using this z-score, right? Comparison of a relative standard similar to both can be made so that they standardize that. Okay. The other thing, let's see if I want to write anything else down. Let's see. So I think I mentioned this before right here, but I'm going to just read this statement just to make sure. So it says here that if the z-score is positive, the person scored above the mean. Okay. If the z-score is negative, the person scored below the mean. Okay, so that's important to stress, and we kind of do say that here. Okay, this is also important. The size of this z-score, write this down somewhere here. The size of the z-score indicates how far away from the mean the person scored. So write that down. And I think we'll be good. I thought there was one more comment I wanted to write, but I don't think so. I was looking for that. Okay, so let's see. So we're going to go and do some calculations. Okay, so so here it says test scores. Okay, so it says that a student scored 65 on a calculus test that had a mean of 50 and then a standard deviation of 10. Okay, so if I start noting that down, and what we're finding is we're comparing the relative positions on the two tests. Okay, so we're going to have to find the z-score then. Okay, so I have z for calculus, so do like a little subscript, and the formula is parenthesis x minus mean divided by s. Okay, so x is our data value. So a student scored a 65 on a calculus test. So that would be your data value minus, and x bar is the mean. So the mean is 50. Remember to put that in parentheses. And then the standard deviation was 10. Okay. So then I can go back also and put right above 65, put x, right about the mean of 50, put x bar. And then right here above 10, I could put a little s there, and that also helps. Okay. Okay, so then when I use my calculator, I'm going to do open parentheses, 65, take away 50, close parentheses, divided by 10. And it looks like that gives me 1.5. And you see it's a positive. So this is 1.5. It represents, it says a number of standard deviations. So this is positive 1.5 standard deviations, and it's above, not below, because it's positive, it's above the mean. Okay. Whereas the other formula is a history test. So you have z sub history. And we already, on the test, you'll have to write down the formula, but we already wrote down the formula and it's the same. So I wouldn't expect you to write it again when you have it here, but make sure you do have it written initially first, okay? And would be your symbol. And you do have to distinguish because there's one for calculus and one for history. So you do need, these are called subscripts. Okay, so then, and then in the numerator, so our x would be a 30 on the test minus the mean was 25, and you're dividing it by the standard deviation, which would be 5. Okay, so again, she scored a 30, that's your x, and the mean is 25, so that's your x bar, and then standard deviation of 5, that's your s. Okay, so then when you put this in the calculator, you have open parentheses 30 minus 25, close parentheses, divided by 5. And that gives you 1. So this is 1 standard deviation. And it's also above the mean because it's positive. If it had been negative, then it would have been below the mean. Okay. All right. So then when you compare the relative positions of the two tests, remember here how I had up here that the larger z-scores have higher relative positions. So that's why we're going to say that she has a higher relative position um, uh, in the calculus class than compare relative positions on the two tests. So she has a high relative position uh, on the calculus. It's a test on the calculus test. And the reason is because the z-score is larger for calculus. The z calculus is larger than the history. Okay, so we're going to write that down. So I'll say she has a higher relative position She has a higher relative position on the calculus test. And the reason why, because oftentimes on the tests, I will also have you justify so that we can do writing across the curriculum, and that will count point. So like if you have a multiple choice test, yes, you would circle the one like, like Z calculus has the higher, but then you have to upload your work, and in your work, I'm checking that you have the symbol, the formula, the substitutions, right? And then you justify, so that would be, all those would count as rubric points. So I'm just not checking like for the like the Z calculus. It involves other things in addition to just circling the right answer. You have to show your work to support that. So part of it would be a justification. So she has a higher relative position on the calculus test because the Z score for the calculus, the Z calculus um, is the larger z-score. Yeah, 1.5 is bigger than 1. Okay, so that's why that works. Okay. Okay, so now let's see what else they have. So let's go to the next page. We got that written down. If not, you can always pause the video and then continue when you're done. Okay, so let me see. This is on page 83 of your workbook, 83. Note that if the z-score is positive, the z-score is above the mean. Okay, if the z-score is 0, the score is the same as the mean. Okay, I had mentioned that. Okay, and then if the z-score is negative, the score is below the mean. Okay, so I just hadn't highlighted that the z-score is 0, the score is the same as the mean. So that's good to remember that. Okay, all right. So which scores indicates the highest relative position? Okay, round your answer to 2 decimal places if necessary. So 2 decimal places, that would be the tenths place. Okay, so you have, your decimal, you have tenths. Excuse me, round to 2 decimal places. Actually, sorry, that's actually hundreds, right? It's actually hundreds, sorry. So you have tenths, and then you have hundreds, and then over here you have thousands. But you have to look at the neighbor, right? If the neighbor is 5 or more, this is 5 or more, then you add 1 to this. So round your answer to 2 decimal places. So that's actually hundredths place, okay? And this is ones right here. Okay, so we have all these scores. So these are all your X's. These are your data values. And then these are all your means. So these are all your scores, your data values. These are all your means. These are all your standard deviations, right? And based on what they're saying, they don't come out and say find the z-score, right? They don't come out and say find the z-score. But based on your vocabulary and relative position, that's what you need to find, the z-score. So you need to know that the z-score where the highest relative position since is the highest. Okay, so we'll try and fill that in with those blanks. But the main thing is we're going to have to calculate this 3 times. Okay, so I have z sub a, right, for the first one. And we need the formula somewhere, so I'll put it up here. The z-score, parenthesis, remember it's data value minus mean, remember, divided by s. Remember we saw that on the previous page. Data value minus mean divided by s, okay? All right. Sometimes people miss it because they wrote the formula down, so you want to be careful. You are required to do the practice test. And on the practice test, of course, you can have the formula on there and you can have a sample, but it is a time test, so you've got to work quickly and know where everything is at when you do that. But you want to make sure you write the formula down correctly. Okay, so then I have x, which is 2.9, take away the mean, which is 4.2, and you divide it by s, which is 1.3. Okay, then you get your calculator. Okay, so parentheses, 2.9 minus 4.2, close parentheses, divided by 1.3 gives us -1. Okay, and this is -1 standard deviations below the mean. This is below the mean, okay? Z sub B, so it's x, which is 620, minus the mean, which is 820, divided by s, which is 220. Okay, so open parentheses, 620 minus 820, close parentheses, divided by 220. Oh goodness, look at that. So it's long decimal. So that's why they say round to 2 decimal places if necessary. Okay, so let's see. 9, 0. Look at the neighbor, which is 9. And I'll put a few others, but we don't really need all those. But here's 2 decimal places, tens, hundreds. Look at the neighbor. Is it 5 or more? Yes. So add 1 to that box digit. So we have about -0.91. And this is still negative, and it's standard deviations, and this one's below the mean because it's a negative, below the mean. Okay. So this one gave us -1. This one gave us -0.91. Okay, and then I can start doing a number line. I will do a number line right here. Okay, so let's say here's 0. Here's -1. Here's -2. Here is -0.5. Here is -1.5. Okay. And the first one, z sub a, was -1. So that's this one right here. Z sub a. The other one is -0.91. So that's real close. This is negative 0.5. So negative 0.5, negative 0.6, negative 0.7, negative 0.8, negative 0.9. So that's about right here. Let me see. So after negative 0.5, negative 0.6, negative 0.7, negative 0.8, negative 0.9. So it's about right here. Okay, then we have z sub c. Okay, so it's x, which is 43, minus x bar, which is 49, and you divide it by s, which is 6. So open parenthesis, 43 minus 49, close parenthesis, divided by 6. Okay, that gives us also negative 1, right? And that's also standard deviations below the mean. Okay. All right. So then what you need to do is you would look at all three of them, and as far as which score indicates the highest relative position, it would be associated with the z-score that's larger. So that's why you look at this. So this negative 1 is also right here. It's the same. This is like for z sub a and for z sub c, right? Both of these are negative 1. And so which one's larger? Well, um, on the negative side of 0, the closer you are to 0, the larger the number is, right? So um, on the negative side only, right, of the number line, on the negative side only of the number line, the closer the number is to 0, then the larger the number, right? So on the only on the negative side of the number line. The closer that little dot, that point is to 0, then the larger it is. So that means that this one is larger. That's the larger z score. Okay, so then z sub b, if I go back to z sub b, here's a z sub b, and then I need the score. See, which score? So z sub b is talking about the score of 620. So sometimes people miss it because all they talk about is the z-score, negative 0.91, but they need to tell me, well, which score, 2.9, 620, or 43, that which score had the highest relative position. Okay, so let's see, where do I write that down? Where do I have room? I'm going to probably have to put it here. So I'm going to have to say that for question 3, I'm going to have to say the score of 620 indicates the highest. I'm going to just say has. You can say it says indicates, or you can say has the highest relative position, and then that's why. Why is that? And that's because um, it has the largest z-score. Okay. And namely, what was it? Namely about negative 0.91. Okay. So I got the score, and then you're justifying why. Why? Okay. Because it had the larger z-score. Okay. Let me see. I think there was also another idea that I'd like to cover. Let me just go back real quick and look at this. Yeah, so we can also, there's another idea here that we can also talk about while we're here, and I don't know if I'm going to see any other problems or not related to that. Let me see what's on 84 though. Let me look at 84. So no, 84 goes into percentiles. Okay. Let me just go back and look at this. There's a reference that you can tell, sometimes you're able to tell if your data values are considered usual or unusual. So, or you know, are they ordinary or are they unusual? And they've got it depends on where your z-score falls. If the value of your z-score, if it falls within a range of -2 to 2, negative between -2 to 2, then your data value, your score is considered ordinary. But if it's outside that range, then it's considered unusual. And I thought I saw today when I was reading this article here, I thought I saw a reference to that 2 and -2, which I wanted to share with you, but I didn't highlight it. So see, I should have highlighted it to see, because I was reading quite a bit. Let me just see if I can find it real quick. There was a reference to 2 and -2. And it's kind of related also to we were doing, Chebyshev's theorem, remember? Also Chebyshev's, and it talks about data value falling within certain parameters, right? So it's kind of related to that. Yeah, I'm not going to be able to find it. I just wanted to read that out loud. Let's see. Okay, I think this is it. Let me read this out loud. I think this is it. Yeah, I think this paragraph is it here. It says, other relative scores. The score on any measure could be converted to a z-score, which would tell you at a glance how a person scored relative to the reference group. Okay, so that may be something good to put down. For example, if someone tells you that her z-score on the exam was positive 1.55, you know immediately that she scored above the mean, and enough above the mean that she is near the top of the class. So remember, here we go. Remember, most of the normal distribution is contained between the boundaries of -2 and 2 standard deviations. That's it right there. There's only about 2% of the area under the curve in each of the tails. If another student tells you that his exam score of Z was a negative 0.36, you know that his score was just a little bit below the mean because it's negative 0.36. With the standard normal table, you could compute the percentile rank for each of these students in a few minutes. Although z-scores are useful and allow people to judge the relative performance of an individual quickly, many people get confused by the negative numbers that are possible with z-scores. So consequently, many tests compute z-scores, but then they translate them mathematically to avoid those, negative numbers. Okay. But let's see, some ideas I can write. Let me go back to the first page. I think what I'll write from that, let me go back to this page. See if I have any room. I think I put it right here. So I like how they said that the score on any measure could be converted to a z-score. Which would tell you at a glance how a person scored relative to the reference group. Okay, and I think that other part, I'm going to just put it on another sheet of paper about that 2 and -2. I don't really have any more room here. Okay, so here we go. We're going to say this. Most of the normal distribution is contained between the boundaries of -2.0 and +2.0 standard deviations. Okay, and that's related like to Chebyshev's. We did Chebyshev's and the empirical rule last section. So it's related to that. That majority of the data, I think the percentage was like 88.89%. I think most of the data fall within 2 standard deviations of the mean. So that's what that's related to. And let's see. can see if I have, let me see if I have that section here, right here. I can show you. Okay, so this is, remember, this is from page 77 of your workbook, and this is part of the Chebyshevs, but it talks about when k is equal to 2 right here, 2 within 2 standard deviations, -2 and +2, right? So within 2 standard deviations of the mean, and then here's just percentage, about 75% of the data. So that's related to that when they say that. So most of the normal distributions is contained between the two boundaries of the -2 and 2 standard deviations, okay, of the mean. And actually, and I'm looking at the word normal. Normal, I could probably also reference, probably should also reference the empirical rule, because Chebyshev is for any distribution. Empirical is normal distribution. And it says fall within 2 standard deviations of the mean. So see, the percentage is higher. See, when you narrow it down to normal, majority of the data, 95%, will fall within that range. Okay, but that's what they're talking about here. So so then what I can also make a comment, I can say that I can say that data values, let me draw this number line here. And let me draw this. So here's, say here's 0, right? And then this is -2 to 2, okay? And so here's 1 and -1. So if you have something that sits within this 2 to -2, it's considered ordinary. But if you have something that sits outside, then it's considered unusual. Was kind of what that means, okay? So you want to tell yourself that, and this has to do with your z-scores. So you make a comment about your z-score. So if a z-score exists within the -2 to 2 range, including it. See, these little bars mean including it, bracket, not parenthesis. If the z-score falls within this range, if the z-score exists within the -2 to 2 range, then what does that mean? That means our data value is considered, you know, ordinary or usual. Okay. But if it sits somewhere outside of that, then it's considered the data value. If your z-score sits outside of that, then your data value is considered unusual. So if we look at the calculations we've done, like let's see. So if we go back to like the calculus problem and the history problem, these were z-scores. So this is a 1.5 z-score and our data value was 65. Okay, so where does 1.5 sit? Well, 1.5 sits like right here, right? That would be about 1.5, right? So that would be your z-score for the calculus. That would be the z calculus score was right here, 1.5. So what does that say about that test score? That test of 65. That's considered usual, okay? So that means that when I write it up, I'll say, I'll ask this, is our data value, which is the calculus test score, right? Is our data value, which is the calculus z-score, excuse me, the calculus test score, is it considered usual or unusual? And then justify your answer. Okay. So you would say our data value, which is the calculus test score, is considered usual. Okay. Ordinary. And why? Why? Because its corresponding z-score, which was what? It was z calculus equals 1.5, right? Because its corresponding z-score, which was this value, is within that range of that -2 to 2 window, right? It was within that window. So that means that it's usual, it's ordinary because it fell within that window. Okay? So I believe on your test you'll have a problem like that. It will reference, you know, it'll have you calculate a z-score and it will also say, hey, does this make your data value, you know, ordinary, usual, or a little peculiar, right? Unusual. So if your z-score falls outside, then that means your data value is unusual. If your z-score falls within this range, then that means that it's ordinary. That's what that means, okay? All right. Okay, so let's see what else they have. So you can, if you haven't finished writing that, you can pause that But that's really what we're saying here. And then while you're finishing that up, let me see what's the next problem. Okay, so now I'm at the bottom of 83. And it says that the average teacher's salary in a particular state is 54,156. So that's your mean, right? X bar, average salary. The standard deviation is 10,420. So that's S. Find the salaries corresponding to the following Z scores. Yeah, that's does looks like they forgot to space that, but the following Z scores. Yeah, these are Z scores. See, Z equals 2, Z equals -2. Okay, so I'm going to just do one of these. I'll just do this first one. But these are all Z's here. So then actually, you have your formula. Z is equal to X. Let me write it over here. Z is equal to parenthesis X minus X bar divided by S, right? So you see, when you're trying to find the salaries, you're trying to find X here. You're trying to solve this for X. Trying to solve that for X. You're trying to find X. So you need to solve something for X. Okay. Now, they give you this formula right here ready. See this formula? We're gonna use that. We're gonna use this formula right here. This finds X. See, this is what X equals to. So X is equal to mean plus Z times S. Okay, so we're gonna use that formula right here. Okay, but I want to tell you how that derived. They're not showing you how they derive. How did we derive that? Where did that come from, right? That actually came from this, the z-score. What they do is they write the z-score over 1, and then they cross multiply. Z times S is, so they cross multiply. Z times S is ZS equals 1 times X minus X bar is X minus X bar. Anything times 1 is itself. And then what they're doing is they're solving for X. So to solve for X, they add this to both sides, plus X bar, plus X bar. And then these fall out because they're additive inverses, and they zero out. Additive inverse, a number plus its opposite zeroes out. So those are called additive inverses. So then this equals X. And then you have these. And these are unlike terms. This is Z times S plus X bar, the mean. And that's what X equals. So, and that's what we have over here. See, let's see right here. They just put the mean first. So I put the mean second, but see, there's your mean plus Z times S. See, Z times S plus that. So that's the same. Okay. So we're going to do one of these. We'll do the first one, but they would all work out the same. Your Z is 2, and your mean for all these problems, your mean is the same. Your mean is 54,000. So this is X equals 54,156. plus z, and in this problem, z is 2. Then you're going to change it to all these, this, this, this. You're going to change that. And then your S is the same for all the problems. Your S is 10,420. Okay, so then X equals 54,156 plus, so if I do 2 times 10,420 is 20,840, and then I'm going to add plus 54,156. It gives me 74,996. Okay. All right. And that would go in this little space here. They already have the dollar sign there, see? All right. So I just want to talk about that because they derived that formula from the z-score, and then they're finding x. Okay, so we can keep an eye on that formula because that's important to note. All right. Okay, let me see. Let me see if let me just see if there's any extra problems. I have a sheet here. Let me see if there's any extra problems I need to do, but I think that covers it. Let me just check this real quick. Let's see. So we already found z-scores. Find the salaries. Okay, so we already did that. We found the salaries. And then we did the one where we looked at all 3 of the z-scores, found the one highest position. Okay, so we're good. We're caught up with that. Okay, so now let's see what else. Let's go to 84. Okay, so let's see what to say about that. Percentiles. So I think I'm going to read. There's something else I want to read to you about percentiles before we do these problems. I'll just look at this. Percentiles. Yes, let me read this to you here. Let me see. I can increase that. Yes, I'm looking at this paragraph right here. So it says that the most basic relative score is the percentile rank, because we're going to be doing a percentile rank in a little bit too, which specifies the percentage of people in the normative group who score lower on the measure than yourself. So if you scored at the 25th percentile, it means that 25% of the people who scored, uh, it means that 25% of the people score lower than you, and then it means that 75% score higher than you. So percentile ranks can range from 0 for the person with the lowest score to 100 for the person with the highest score. Okay, so I wanted to mention that about percentile ranks. Um, the other thing I wanted to mention, here's just another good reference idea here. Let's see. This says that when you take an exam, okay, it says when you take an exam, what is often as important as your actual score on the exam is the way you score, the way your score compares to other students' performance. So if you made a 70, but the average score, whether the mean, the median, or the mode was 85, you did relatively poorly. Okay, so if you made a 70, but the average score was for the class was 85, okay? But if you made a 70, but the average score was only a 55 average score, then you did relatively well. So in general, the significance of one observed value in a data set strongly depends on how that value compares to other observed values in a data set. Therefore, we wish to attach to each observed value a number that measures its relative position. Okay, so it's kind of what we're looking at, right? And then now we're going to percentiles. So this is another good paragraph to share with you here. Percentiles and quartiles. So anyone who has taken a national standardized test is familiar with the idea of being given both a score on the exam and a percentile ranking of that score. You may be told that your score was 625 and that it is the 85th percentile. The first number tells how you actually did on the exam. The second says that 85% of the scores on the exam were less than or equal to your your score of 625. Okay, so that's another good idea to share with you. Okay, and in this one I do have another idea here which I'm going to share, and this one should be in your documents. If you look at your documents in your test one module, I believe I have something like this. These are like extra problems. But you see, we already did one like this already, and we just did this one a while ago. So we've already done these. These are extra problems. We've done these, covered these. So we're kind of like here now. But as far as this vocabulary goes, let's see. So this is what we were talking about. We wrote down the z-score of its unusual. This is where this came from. When all data for a variable are transformed into z-scores, then the resulting distribution will have a mean of 0 and a standard deviation of 1. Unusual data values are those with z-scores that are less than -2 or greater than 2. So if you're sitting out here, then that makes your data value unusual, okay? Such z-scores imply that the data values are or usual or ordinary. If they sit in here, if your z-score sits in here, then your data value is considered usual or ordinary. Okay, so we went over that, and then here's more about the percentiles. Percentiles are not the same as percentages. If a student gets 72 correct answers out of a possible 100, then he or she obtains a percentage score of 72. There's no indication of his or her position with respect to the rest of the class. But the student could have scored the highest or the lowest or somewhere in between. We just don't know. But if you have a raw score of 72 corresponds to the 64th percentile, then this means that the student actually did better than 64% of the students who took the same assessment. Because remember what they said earlier, they said the reference they said over here was, let's see when I read that. Here. "85% of the scores on the exam were less than or equal to your score." Okay. So yeah, so this means that on this 64%, 64th percentile, that means the student did better than 64% of students who took the same assessment. Okay, so I think I like it word. They both say the same thing, but I think I do prefer how this is worded here. So percentile has to do with the position in the hundreds that a data value holds in the distribution. They call that P sub n. But the percentile is a relative measurement of position. Okay, so you want to write this down, because this is, I think, on your test you have some multiple choice on the first part of your practice test, and that's related to this vocabulary. Percentile is a relative measurement of position. A percentage is an absolute measure of the part to the total. Okay, so go ahead and pause and write that down, and that'll be part of your vocabulary for your review on your tests. Okay. So you can pause that and write that down, and then also could pause right now and then write that down. Okay. So we talked about this earlier. So pause it and write that down. Pause and write that down. Okay. All right. And then I'm actually going to take a break. And when we come back, and then I'll do the next part, which is the next page, which talks about percentiles, and now that we've gone over this. Okay.